Well, hello everybody. This is Inan Ulusoy from Turkey, and I'm going to present you our thermal infrared remote sensing study on Hasandağ volcano in central Anatolia. This is Central Anatolian volcanic province, which also hosts Mount Erciyes, Cappadocia, Göllüdağ, and Acıgöl calderas. And at the southernmost part of this area, we have Hasandağ system. The Hasandağ system is composed of two stratovolcano cones called Greater Hasandağ and Lesser Hasandağ, which are rising inside an earlier caldera structure. Here you see a photograph from Güzelyurt village at northeast. This is Greater Hasandağ and this is the Lesser Hasandağ summits. So we have successive construction and collapse events on the system. We have Holocene eruptive activity, which is also depicted on a wall painting in Çatalhöyük, a Neolithic site southeast from Turkey, from the volcano. And we also have a lava dome, which was dated 6,000 years ago as well. This eruptive activity was almost 9,000 years ago. Both cones present fresh cone morphology when compared to the other central Anatolian volcanoes. We have geophysical evidence that we have hydrothermal activity on both of the Greater Hasandağ and Lesser Hasandağ summits. This is a self-potential map from thesis of my former PhD student Can Erdiker, and we have distinct anomalies on both summits. And we also have a fumarole zone at the western flank of the Greater Hasandağ summit. We have several weak steam vents between 3,000 and 3,100 meters, and the ground is hot when compared to the surrounding area in that zone. We have alteration mineralization. The maximum temperature we measured in those vents was 70 centigrade degrees, and time to time we measured carbon dioxide values hitting 100,000 ppm with an infrared sensor though. So we try to test if we can monitor this hot thermal zone using thermal infrared imagery. So we tested both MODIS and ASTER instruments, and we also had a thermal camera mounted on a drone to acquire high resolution imagery. So this is MODIS day to nighttime surface temperature data. This is data from 2000 to 2018, daily surface temperature data over the fumarole area on the summit zone. So we decomposed this data into its seasonal and trend and reminder components. This is a statistical method used mostly for finance area for decomposing time series data into its periodic and non-periodic components. So this is seasonal data, and this is the trend data which we can refer to as surface temperature and anomalies in that zone. So we have a slightly increasing general trend in the area. This is the global warming, which is also consistent with the values of the global warming in the area. And we have both positive and negative +2 to -2 centigrade degrees fluctuating anomalies here. So to test if this is a real anomaly, we compared it with the meteorological data from a meteorological station 30 kilometers away from the volcano. So what we have is that we have similar trend values along this time, and which means that the data is quite comparable with meteorological data, and those small anomalies are mostly related with the meteorological events. Here we normalize the trend data, compare them with each other, and take the difference of them. Here also you can see the surface temperature anomaly and relative radiative heat flux calculations from Aster images on dots. So this is the Aster imagery. We used Aster imagery mostly to map the thermal zone in the area. So we used Aster level 1B thermal infrared data. We calculated the surface temperature, and then we removed the topographic components, and we calculated the surface temperature anomaly. And at the end, we calculated relative radiative heat flux, also by integrating the upper air sounding data to the thermal remote sensing data. And we calculated those values for 56 Aster nighttime imagery through 18 years period. Here you see them as surface temperature anomaly, and relative radiative heat flux within the year and within a period of 18 years. So the red dots here are the summertime images, and the blue dots are the wintertime images. You can see there are some sole anomalous values, but they are not continuous in time. And this is the summit zone. This is the anomaly we observed in the summit zone. Not clear at every image, but we have those anomalies at some images on the Aster thermal imaging. We also used the drone-mounted thermal camera to map the area in high resolution. So this is the anomalous area. These are the points where we observed the vents, and this is an image from ground, looking directly into the fumarole zone. You can compare the size of the tent with the area. So all the vents are aligned along a crack zone, which we think is related with the Karacaören fault on the volcano. So this is a stereophotogrammetric image of the summit area. The yellow dots here are the thermally anomalous dots, and the related crack fault zones are mapped here. Thank you for listening. I hope I may be joining you in the future in person, and we are looking forward for collaborations to work on Mount Hasan for deeper geophysical studies. See you all.